AP Chemistry. This is lesson 4 in Unit 7. It's the last lesson of Unit 7, covalent and ionic bonds, and this lesson is on formal charge and resonance. So we know that oxygen in its atomic state is a neutral atom with 6 valence electrons. So there's the Lewis diagram of an oxygen atom. Formal charge is a way of determining the charge on an atom involved in a covalent bond. If the formal charge is different than the normal valence charge of the atom, 6 in the case of oxygen, then the atom and overall molecule will be less stable. Nature prefers the most stable configuration of a molecule. So the formal charge of an atom is given by the formula. Formal charge equals the number of valence electrons that atom naturally has, minus the number of lone pair electrons that it has in the molecule in which it's attached, minus 1/2 of the bonding electrons in the molecule in which it's attached. So that formula will become clear after a couple of examples. So example. Both of the following configurations can be formed using the rules of covalent bonds that we learned in the last lesson. So if you take a look at those two molecules, both of them use 16 valence electrons. That's how many are contributed by 2 oxygens and 1 carbon. And they all have full octets. Every atom has a full octet. So both of those particular configurations of a carbon dioxide molecule meet both of the rules that we learned about in the last lesson. So how do we know which one is actually going to be formed in nature? Well, what we're going to do is take each atom one by one, and we're going to use that formula up above to compute the formal charge on that atom. So we start off with the oxygen on the left, and it has 6 valence electrons. Any oxygen has 6 valence electrons in its natural state. Then if you look at the oxygen, specifically the one on the left, it has 4 lone pair electrons. It's not how many lone pairs. There are 2 lone pairs there, but it's how many actual electrons. So there's a total of 4 lone pair electrons in that red box. And then you take half of the bonding electrons. And there are 4 electrons bonding the oxygen to the carbon. You take half that number, so that would be 2. So if you add, or subtract rather, take 6 minus 4 minus 1/2 of 4, you get 0. So that's a very stable atom there because it has a formal charge of 0. So oxygen has 6 valence electrons, oxygen has 4 lone pair electrons, and we take half the bonding electrons, we get 0. Now we're going to look at the carbon in the middle. Carbon in its natural state has 4 valence electrons. There are no lone pair electrons on that carbon, and there are 8 total bonding electrons, of which we take half. So 4 minus 0 minus 1/2 of 8 equals 0. So that carbon is very stable in that configuration. Carbon has 4 valence electrons. Carbon has no lone pair electrons, and we take half the bonding electrons. Now we're going to look at the oxygen on the right. Oxygen has 6 valence electrons. The 4 electrons you see in the red box, 4 of them are lone pair electrons, not attached to any atom, any other atom. They're not bonding 2 atoms, in other words. And then 1/2 of the 4 bonding electrons between oxygen and carbon. The reason for the 1/2 is it's the way this formula works. It assumes that half of those bonding electrons belong to oxygen and half belong to carbon. Even though we know in a covalent bond they're totally shared, this is the way the formula works. So oxygen has 6 valence electrons, oxygen has 4 lone pair electrons, and we take half the bonding electrons, and we again get 0. So if we take all 3 of those, we have 0, 0, 0, and that is that's as stable as you can get, is to have all zeros for the formal charges of all of the atoms. Now we're going to take a look at the configuration on the right. So the formal charge of 0 on all elements means that this configuration of CO2 is stable. So now we'll look at the oxygen there. The left on the carbon dioxide molecule on the right, we'll take a look at the left oxygen. So oxygen always has 6 valence electrons. You see that 6 of those electrons in the red box are lone pair electrons. They're not bonding to another atom. And that 2 are the bonding between oxygen and carbon. So you take 1/2 of those 2, and now you get a -1 here. It's not a 0, it's a -1. That means that oxygen is not as stable as it could be. Oxygen has 6 valence electrons, oxygen has 6 lone pair electrons, and we take half of the bonding electrons. So the -1 charge on the left oxygen means that it is less stable than a 0 formal charge element. Now we'll look at the carbon, and we see that it's definitely a different configuration around the carbon on the right than the one on the left molecule. So carbon has 4 valence electrons. It has no lone pair electrons, that's the 0, and 1/2, it has 8 bonding electrons, and half that number is 4. So you still get 0 with the carbon. So the carbon is still very stable, even though it looks definitely different than the molecule on the left. So carbon has 4 valence electrons, carbon has no lone pair electrons, and we take half of the bonding electrons. And now we'll look at the oxygen on the right. So there it is right there. So oxygen has 6 valence electrons, 2 of them are lone pair, and 6 are bonding it with the carbon. So you take half that number, so 6 minus 2 minus 1/2 of 6 gives you +1. It doesn't matter whether the formal charge number is positive or negative. It's simply the fact that it's not 0 means that it's not as stable as it could be. So now we take all those and we see that we have a -1, a 0, and a +1. So since we have non-zero formal charges on 2 of those atoms, that means that configuration of carbon dioxide, the one on the right, is not as stable as the molecule on the left. Now, you may notice that the formal charges for the molecule on the right add up to 0. They do add up to 0, -1 plus 0 plus +1. That's always going to be true if the molecule doesn't have a charge and carbon dioxide does not have a charge. The formal charges will add up to 0. If it was some kind of a molecule that was an ion, like say SO4 that has an ion, then the formal charges would add up to whatever the charge on the overall molecule is. So just because the formal charges add up to 0 doesn't make it stable. The fact is that 2 of the 3 formal charges are not zeros, and therefore that molecule is not going to be as stable as the one on the left where all 3 formal charges were 0. So both oxygen atoms have a charge. This makes the molecule on the right less stable than the molecule on the left. So this is the configuration of CO2 in nature. Nature will not form the configuration that you see on the right-hand molecule. Now we're going to take a look at a concept called resonance structures. A resonance structure is an alternate construction of a molecule. Ozone has a formula of O3. Ozone contains 3 oxygen atoms. The central atom is connected to one of the terminal atoms with a single bond and the other with a double bond. But how do you know which is which? Who says that the oxygen on the lower left should have the double bond rather than the oxygen on the lower right? It really could be either one. So one way you can draw or symbolize resonance structures is to draw both of those possibilities and then put a double arrow between them to say that that's the resonance structure. There's another way to do it. Since the double bond could be connected to either the right oxygen atom or the left oxygen atom, it can be shown in both configurations with an arrow between them. So here's an alternate way to show a resonance structure. A resonance structure is an alternate construction of a molecule. In nature, however, the second pair of electrons in the double bond is moving throughout the molecule. So remember that double line, that double bond, means you have two additional electrons. And in nature, they're actually going to move all throughout the molecule, not just stay on one side or the other. So this is similar to the electrons in a metallic bond, which they fly all over the place and move around between the atoms. So they are said to be delocalized. Ozone can be thought of as having 1.5 bonds represented by a solid and dashed lines. So both sides, this is the way you show them as being equal, is that you show, instead of showing a double bond on one side and a single bond on the other, you just show it as a 1.5 bond, because that second pair of electrons is going to be moving back and forth between the two sides. And that takes care of this lesson. That's all for this lesson. So we'll practice some of these, and that will conclude our lesson on covalent and ionic bonds.